Welcome to this MECC 2021 online presentation. My name is Balint Patartic and I work in the Institute for Computer Science and Control in Hungary. I've been working on this topic with Bálint Vanek, Béla Takarics and Jais Kumtepe from Rocketsan. We also acknowledge funding from the EU project FLIPACE. In this talk, I'm going to give recommendations on when flexible modeling is required for the fall detection of a flexible aircraft. This is the block diagram of the fall detection problem. We have a flexible aircraft with a set of sensors and actuators. We consider two faults in the system. The elevator actuator and the angle of attack sensor may fail. These faults are represented as additive disturbances on the corresponding signals. Measurement noise is also taken into account. We assume that the aircraft operates in closed-loop control, but the actual controller is not part of this discussion. Using the values of the actuator commands, the measured outputs, and the model of the aircraft, we want to design a filter that calculates an estimate of the fault signal. This estimate is usually called a residual. To use one of the modern, model-based optimal design techniques, such as H-infinity synthesis, we need an appropriate model of the aircraft. A rigid model that doesn't take the flexibility of the airframe into account is obtainable by well-known and traditional techniques. A flexible model, on the other hand, requires special expertise and is in general more difficult to construct. Hence, in this talk we explore the limits of using a rigid model when designing a fall detection system for a flexible aircraft. We do this by synthesizing an array of filters with different bandwidths for both models and calculating the smallest detectable fault and detection time as a function of the bandwidth. Using this data, we establish the performance thresholds below which a rigid model is sufficient. This is the outline for the rest of this talk. First, I'll introduce the flexible aircraft in question. Then, I'll explain the H-infinity filter design setup. At this point, the two performance measures will be defined, which are used to evaluate and compare the different filters. These are the smallest detectable faults and the detection time. Then, we'll look at these performance measures as a function of filter bandwidth. Finally, based on this analysis, I'll give some recommendations on when the use of a rigid body model can be satisfactory. Our case study revolves around the flexible aircraft depicted here. It was built for the FLIPACE project. To give you an idea of its dimensions, the wingspan is 7 meters, the aspect ratio is 20, and the takeoff weight is between 55 and 65 kilograms. This is the aircraft from a top view. It features a single jet engine and two pairs of rudder vators on the V-tail. We want to detect a fault in the rudder vators that affect the longitudinal motion of the aircraft. Therefore, the rudder vators are transformed to a single elevator in the model. For the rest of this talk, I refer to this control surface as elevator for simplicity. The aircraft is also equipped with an air data probe with which the speed and the angle of attack are measured. There is an inertial measurement unit, or IMU for short, in the center of gravity, where the pitch angle, pitch rate, and vertical acceleration are measured. Also, the local acceleration and pitch rate are measured close to the wingtip by another pair of IMUs. These make up the sensors and actuators that are significant from the fall detection point of view. In this analysis, we will compare filters designed using two sensor configurations. The first set of sensor signals have no acceleration measurements, hence we will refer to them using the label no ACC. In the second set, we use all of these signals and the acceleration measurement at the center of gravity, and also the IMU signals close to the wingtips. We will use the label ACC to refer to the case when these measurements are also included. As I mentioned before, we consider two aircraft models, a rigid model and a flexible model. The rigid model is detailed in standard textbooks such as the one highlighted here. The modeling or identification techniques required to construct such a model are widely used and are accessible to a control engineer. The complete model has 12 states, Euler angles, angular rates, coordinates and velocities along the three coordinate axes. For our fall detection problem, only the longitudinal model of the aircraft is needed, which has 4 states. On the other hand, the process leading to a flexible model is fairly complex and requires special expertise. The specific model we use for this study is detailed in these papers. The complete model has over 600 states. This complexity makes the model intractable for control design purposes. Hence, model reduction is required that results in a longitudinal model with 16 states. Also, this model is trimmed and linearized at a certain speed to obtain a linear design model. For this study, we residualize the flexible states of this reduced linear longitudinal model to obtain the rigid longitudinal model. We do this to make the differences between the models solely stem from the flexibility. This way, they are comparable. In practice, the rigid model is the result of an independent process. Let us now focus on the H-infinity filter design. This is the generalized plant interconnection. The aim of the H-infinity synthesis is to find a filter F that minimizes the H-infinity norm of this interconnection from the external disturbances to the weighted error signal. Notice that we designed a single filter to detect both faults because we also want to study the coupling between the two. The plant here is either the rigid or the flexible longitudinal model of the aircraft. We introduce input multiplicative uncertainty into the system to account for high-frequency neglected dynamics. The weight of the uncertainty W delta is chosen as follows. On this diagram, you will see the magnitude of the weighting function as a function of frequency. This is the elevator actuator. The weight of the uncertainty is chosen to represent 30% uncertainty on low frequencies, 100% uncertainty at high frequencies, and about 50% uncertainty at the bandwidth of the actuator. The filter design is formulated as a model matching problem. T here represents the desired response of the filter to the faults. It is chosen as a low-pass filter with no coupling between the two fault signals. Kappa is a design parameter that expresses a requirement for the filter bandwidth. Choosing kappa equals 1 second, this is the magnitude of T. The difference between the desired response and the actual residual is weighted by WE. WE is also parameterized by kappa, and it is chosen to match the bandwidth of T. The measurement noise is weighted by Wn. This weighting function expresses the noise cancellation requirement as a function of frequency. This is Wn. R is a diagonal matrix with the standard deviations of the individual noise signals on the main diagonal. We design an array of filters for different values of kappa and for both the rigid and flexible model to study the attainable performance as a function of the filter bandwidth. This interconnection is the system we analyze. It is similar to the generalized plant, but with the weights removed. The uncertainty is included because we want to take it into account by conducting worst-case analysis. Also, we conduct the analysis for several values of the filter to obtain results as a function of kappa and consequently as a function of the filter bandwidth. In each case, we use the flexible aircraft model for the analysis. The whole interconnection from the external output to the residual is denoted by T delta and S. The dependence of T on the uncertainty is emphasized by the notation. We now define the performance measures used to evaluate the fault detection, the detection time and the smallest detectable fault. Both quantities are defined for one fault only because the generalization to the case when there are two faults in the system is straightforward. Consider the response of the fault detection filter when a fault such as this is injected into the system. When there is no measurement noise, we get a residual like this. The effect of the control command to the residual is measured by the maximum DC gain of T from the control input to the residual over the set of admissible uncertainties. When we calculate theta, we get a value like this. We use the approximation that if there is neither noise nor fault in the system, then the residual produced by the control command alone is below theta for all allowable uncertainties. When measurement noise is present, the residual looks more like this. The effect of the noise on the residual is captured by the standard deviation of the residual. This is calculated by the H2 norm of T from the noise input to the residual. The noise inputs are also weighted by the matrix R with the standard deviations of the noise channels on the main diagonal. Because of the way the uncertainty enters into the problem, the uncertainty doesn't affect the channels involved in this calculation. Therefore, delta equals 0 is substituted into t. We use a simple threshold decision logic to decide whether a fault occurred in the system. In the actual implementation of a fault detection system, an integration based or an up-down counter based decision logic is usually employed. Our simple threshold logic approximates the behavior of those more complex solutions. The decision threshold is the maximum residual caused by the control input plus one standard deviation of the residual signal. The detection time is the time it takes for the residual to cross the threshold when there is no measurement noise. When the steady state value of the residual is theta plus 1.3 sigma, then the probability that the residual is above the decision threshold in steady state is 90%. Therefore, we call the corresponding fault the smallest robustly detectable fault. Instead of the design parameter kappa, we want to express the analysis results in terms of filter bandwidth. We define the bandwidth as the frequency beyond which the gain of the filter is less than minus 60 decibels. For example, if the gain of the filter as a function of frequency looks like this, then we find the frequency where the gain crosses the minus 60 decibel line and call that frequency the bandwidth. If the gain of the filter looks like this, then this is the bandwidth. When the gain crosses the minus 60 decibels line multiple times, like this one for example, then we pick this frequency as the bandwidth. We define the bandwidth like this to ensure that the frequency response of the filter beyond this frequency is truly negligible. Let us finally look at the results. First, we will see the smallest detectable fault as a function of the filter bandwidth for the elevator fault detection. Two notable frequencies are marked on the frequency axis. Omega SB is the frequency of the short period mode, which pertains to the rigid motion of the aircraft. Omega FB is the frequency of the first bending mode of the wing, which corresponds to the flexible behavior. This is the curve we get when we design the filter for the flexible model and use the acceleration measurements. Hence, this is the best performance we can achieve. The curve is increasing since the speed and the accuracy of the detection are at odds with each other. When we design the filter using the rigid model, the trend we see is similar to the previous case, up to half of the frequency of the short period mode. Above this frequency, the difference between the models is becoming more significant, causing the disparity in the performance. When the acceleration measurements are not involved in the design, the performance is uniformly worse than in the ideal case, but it degrades much less above omega SB/2. The values are only plotted up to this point because here the filter bandwidth jumps to unrealistic values. This is also the case when the design is carried out using the rigid model. Note that while without the acceleration measurements the achievable performance is limited, it isn't impacted by the choice of the design model so heavily. Let us also look at the detection time as a function of filter bandwidth. This is the best attainable performance using all the sensor data and the flexible model. Naturally, the detection time decreases with the filter bandwidth. Just like with the smallest detectable fault, it is possible to recover the best performance with the rigid model when the acceleration measurements are used up to omega SB/2. Beyond this frequency, the two curves diverge sharply, however. If we look at the two no acceleration cases, we conclude that optimal detection times are achievable with the rigid model-based design if the acceleration measurements are omitted. This is only true up to the neighborhood of the frequency of the first bending mode, beyond which the use of the flexible model is necessary. The angle of attack sensor fault detection is not very much affected by the model uncertainty, nor by the choice of the design model. The best performance is again achieved when the flexible model and all the sensors are employed. The switching to the rigid model doesn't result in a significant change. Even when the acceleration measurements are omitted, the performance curves stay relatively close together. We conclude that good performance is attainable using the rigid model with the acceleration measurements. For the detection time, the curves are very close to each other for all cases. A reasonable choice is again the rigid model with the acceleration measurements. Let me finish by summarizing our findings as recommendations for the choice of design model and sensor configuration. Based on our observations, the proposal is divided into 3 frequency ranges. When designing the elevator fall detection filter, good performance is attainable using the rigid aircraft model with acceleration measurements in the low frequency range up to about half the frequency of the short period mode. The performance is also acceptable with the rigid model in the mid-range up to roughly the frequency of the first bending mode if the acceleration measurements are omitted. Above this frequency, the flexible model and all the sensor signals are required. For the angle of attack sensor, the recommendations do not have to be divided into frequency ranges. The rigid model-based design with acceleration measurements achieve uniformly good performance. If you're further interested in this topic or have any questions, please feel free to contact me. Thank you for watching, and I hope to see you in future conferences.